Hey everyone, this is Mike Bartles from HEC. Within this presentation, I'll continue discussing the Clark unit hydrograph parameter regression equation analysis that we recently completed for the state of California. This video is part 2 within a series of videos devoted to this analysis. As an overview, within this video, I'll present on how we selected locations that were used within this analysis, how input data was compiled, and the methods that were used to construct and calibrate 100 plus HEC-HMS models. Same as the last video, if you know which dam or river this is, please write it in the comments. California is home to approximately 40 million residents and has a land area of approximately 155,000 square miles. Within California, you can easily find extremely diverse geography, ranging from the Pacific coast in the west to the Sierra Nevada mountains in the east. In the northwestern portion of the state, coniferous forests are prevalent while the Mojave Desert can be found in the southeast. Additionally, the approximately 50-mile wide and 450-mile long Central Valley stretches across the center of the state. Similar to geography, the climate within California is also tremendously varied. A Mediterranean climate is prevalent through the Central Valley, while moist temperate rainforests can be found in the north. Additionally, arid desert regions are widespread in the southern half of the state, while snowy alpine areas can be found within the Sierra Nevada mountains. All this is to say that deriving one or two regression equations to predict all the Clark unit hydrograph parameters throughout the state is difficult, to say the least. Thus, we divided the state into 10 regions using 4-digit hydrologic unit codes. These regions are shown here. 100 locations, corresponding to either USGS stream gauges or USACE reservoirs, were chosen throughout the 10 hydrologic regions to develop the Clark unit hydrograph parameter regression equations. Approximately 10 locations were chosen within each region. However, due to a lack of available observational data, some regions contain fewer or more than 10 locations. Attempts were made to choose locations that were unimpacted by the effects of impaired flow, but due to the widespread use of regulating structures like dams and diversions throughout the state, some locations were impacted by impaired flow. These effects were investigated and quantified for each location, and only those that demonstrated minimal impacts were selected for use. Now let's talk about how HEC-HMS projects were created for all 100 locations. First, we created a standard operating procedure, or SOP, that could be used to construct and calibrate HEC-HMS models in the same consistent manner. Then we assembled a large team of modelers from HEC, as well as the San Francisco, Sacramento, and LA districts. Each of the 100 locations was assigned to a team member in order to collect and process data, as well as construct and calibrate the HEC-HMS model. The intent was to go from nothing to a calibrated HEC-HMS model within approximately 1 day. For each location, multiple sources of GIS, boundary condition, and observed data were gathered. Information such as terrain, hydrography, gridded precipitation, stream flow, and computed reservoir inflow were used to construct and calibrate each of the HEC-HMS projects. The items with asterisks were only required if a selected location was appreciably impacted by snowmelt. Stream gauges operated by the U.S. Geological Survey, in addition to reservoir gauges operated by USACE, were used to identify locations with observed data. Observed streamflow data at USGS projects were downloaded from NWIS. Observed reservoir data from USACE projects was downloaded from Core Water Management System, or SWIMS, servers at the Sacramento and Los Angeles districts. Inflow to these USACE projects was computed using change in storage and observed outflow. Multiple sources of gridded precipitation were used. The gridded precipitation data source that was used for each modeling domain depended upon the age of the event used for model calibration. For instance, MRMS data was used for events that occurred after 2015, such as the animation that is being shown here for the Middle Fork Eel River watershed. In all instances, sub-daily precipitation was initially used to best capture the temporal distribution of precipitation. The gridded data import tool within HEC-HMS was used to import the data, reproject to the desired coordinate reference system, resample to a 2-kilometer grid size, and clip to the boundary of the modeling domain. Following the import process, the sub-daily gridded precipitation data was contrasted against the PRISM dataset. Precipitation mass curves were calculated for both the sub-daily and PRISM datasets, and then compared in order to ascertain whether the sub-daily precip, which better captures the temporal distribution of rainfall, adequately captured the cumulative volume of precipitation, which is best described using the PRISM dataset. The image above shows an example where the sub-daily precipitation underpredicted the precipitation accumulation during the time period of interest and required normalization. Multiple sources of gridded temperature and snow data were used when a location was impacted by snowmelt. Similar to precipitation data, the selected temperature and snow data source depended upon the age of the event used for model calibration. Once all relevant data was collected, an HEC-HMS project was created, and the required components like a basin model and a meteorologic model were created as well. The same modeling techniques were used for each location. This consisted of structured discretizations, deficit and constant losses, Clark unit hydrograph transforms, linear reservoir base flow, and gridded temperature index snowmelt when required. Again, this was only required if a location was appreciably impacted by snowmelt. Multiple directly measurable and indirectly measurable watershed characteristics were evaluated for the contributing drainage areas at each location. These characteristics included the drainage area, longest flow path length, centroidal flow path length, 1085 flow path length, 1085 flow path slope, basin slope, basin relief, relief ratio, elongation ratio, drainage density, L times the square root of S, basin shape factor, and L times the square root of drainage area times S. HEC-HMS was utilized to extract these parameters for each location, and this was done in preparation for eventual use in the derivation of the regression equations, which each utilized one or more of these parameters. It was anticipated that DSOD were going to utilize these regression equations to estimate Clark unit hydrograph parameters to simulate extreme events within dam safety studies. As such, extreme storm events were selected for use during model calibration. However, observed data availability, reliability, and ease of use were also considered. Observed data that was available for use varied by location and flood event. When available, 15, 30, or 60-minute observed stream flow data was used. When that data wasn't available, daily average and instantaneous peak stream flow data was used. Finally, when all other data was not available, only the instantaneous peak stream flow data was used. Model performance was evaluated by comparing computed results against observed results at each location. Model parameters were then altered to minimize the differences between computed and observed hydrograph shape, peak flow rate, and discharge volume. When adequate observed data was available, at a minimum daily average stream flow, summary statistics were used to quantify model performance. Statistical metrics included Nash Sutcliffe efficiency, ratio of the root mean square error to the standard deviation, and percent bias. Following calibration, we collected data from each of the 100 HEC-HMS projects. Now, these are histograms showing all 100 calibrated times of concentration on the left and watershed storage coefficient values on the right. It's important to cover a wide range of possible parameters, such that the regression equations that are developed are robust over an equally wide range. In summary, within this video I detailed how locations were selected throughout the state, how various sources of data were compiled for use, and how HEC-HMS models were developed and calibrated. In subsequent videos, I'll talk more about the regression equation development that was completed as part of this analysis. Thanks for watching. I'll see you in the next one.